my name is Chris Randall, and I'm a master's student here at SF State studying statistical data science. And currently, I'm doing research with my advisor, Serkan Hostin, in the field of algebraic statistics. Specifically, I'm looking at things called algebraic Gaussian models. So for what an algebraic Gaussian model is, if you have a normal distribution, such as this two-dimensional one, which you can see has the characteristic bell curve shape, an algebraic Gaussian model is a statistical model that parametrizes these normal distributions. And specifically, I'm interested in studying these through the lens of what's called convex algebraic geometry. So convex geometry is related to shapes like this one, which is a disk, and it's convex because for any 2 points, the shape contains the chord between those 2 points. And convexity is important in statistics because convex optimization problems are very well understood, whereas non-convex optimization problems, like the ones that show up in machine learning, are very difficult to understand. On the other hand, we have algebraic geometry, which is the study of shapes cut out by polynomials. So this one, for example, is cut out by y squared equals x cubed plus x squared. And on the surface, these look like very different topics. Algebra and convexity seem to have very little to do with each other. But if we sort of fill in this shape here, we actually get a convex shape whose boundary is algebraic. And so we can study this through the relatively new field of convex algebraic geometry. And it turns out that these sort of convex algebraic shapes show up quite a bit in statistics. So my favorite example is what's called the elliptope. So it's this example here of the shape that you can see kind of looks like a puffed tetrahedron. And this parameterizes what are called unrestricted correlation models. And what we'd like to do is study the convex geometry of the shape and use it to understand the statistics of those models. And there's two main ways to do this. One is through what's called a maximum likelihood estimator. And I've studied some properties of these, and I've proven some convexity results for these maximum likelihood estimators. And the other way to do this is through what's called a Voronoi diagram. If you've seen Voronoi diagrams before, you've probably seen that they have these kind of interesting sort of cellular shapes, and it's based on the Euclidean distance between different points. And you can do something analogous with a statistical model using a statistical notion of distance. You get these things called log Voronoi cells, which can have these very interesting shapes, like you see here. And in particular, recently I've been studying the sort of boundary between this green region and this red region and trying to disprove certain conjectures related to that. And so in general, I'm trying to understand the convex algebraic geometry of statistical models in order to better understand their statistical properties. And thanks to the ARCS Foundation, I've not had to have a second job. And so I've had plenty of time to do research on this topic. And so I'm very grateful to the ARCS Foundation.